Introducing Project Altair by Team Foxtrot. The drone manufacturing team from Ghulam Ishaq Khan Institute, Pakistan. Altair is the proposed unmanned aerial vehicle for the 2023 SUAS competition and is designed to carry payloads and travel long distances to aid in the challenge missions. It can be utilized for a wide range of applications such as aerial mapping, surveying, and rescue missions, as it is equipped with advanced sensors, imaging, and navigation systems. The team consists of students from various engineering disciplines and is divided into four main streams: design, product development, software development, and multimedia, who work passionately to unveil the possibilities in aviation every day. Our competition team includes Muhammad Ali Khwaja, who is our team manager and director of automation. He is also the safety pilot and point of contact and has 4 years of experience. Waliullah Khan, who is our team's director of design and test pilot as well as the GCS operator and backup safety pilot and has 4 years of experience. Umar Arif, our team's product and systems development lead and multimedia lead and has experience of 4 years. Zain Mahmood, our team's director of testing and documentation and the competition safety and operations lead with 4 years of experience. Hashim Shabir, our team's product development head and competition's electrical systems lead with 3 years of experience. Moiz Taha, our team's director finance and design head as well as the GCS operator and electrical systems lead with 3 years of experience. Muhammad Ahmed Adil Khan, our team's design and automation lead and mechanical systems lead with 3 years of experience. Muhammad Danish Javed, our team's digital graphics lead and electrical systems head, as well as multimedia and avionics lead with 3 years of experience. Abdur Rafe Amir, our team's automation systems head and product assembly lead with 2 years of experience. Abdul Wase, our team's product development head and electrical systems and product assembly lead with 2 years of experience. Muhammad Saad Farooq, our team's mechanical systems lead and avionics lead with 2 years of experience. Umar Irfan, our team's automation head and avionics lead with 2 years of experience. Altair is designed and tested to comply with all the requirements set by AUVSI to score the maximum possible points. Altair has a maximum takeoff mass of approximately 40 pounds, which is within the 55-pound limit. Safety Pilot and GCS have been deployed according to challenge requirements. LiDARs are used for obstacle avoidance, which will continuously monitor the surroundings to timely perform evasive maneuvers. Electronics and payload are very well secured in place on the UAV to avoid any debris falling off during the mission. A high-definition 3-axis gimbal is used to make the airdrop as accurate as possible within an allowed 15 feet radius. 20 test flights were performed, and the maximum waypoint deviation was 12 to 15%, which is within the allowed limit. Using two 6S 30 amp-hour batteries in series, the drone has a flight time of approximately 40 minutes and can go more than 12 miles on a single flight. 113.8 pound force of total motor thrust, approximately 19 pound force each, is enough to carry the UAV to an altitude of at least 75 feet. Our chosen airframe is a modified Effertec X6120, a hexacopter frame with 0.63 inches of carbon fiber tubes used for arms and landing skids. The system utilizes 6 T-motor MN605S 170 kV motors with 22.4 by 8-inch propellers, combined with two 30 amp-hour 6S batteries which provide a thrust-to-weight ratio of 2.8 and a top speed of 19.44 knots while having a maximum takeoff mass of approximately 40 pounds. For autonomous flight, our system uses a CUAV X7 Plus flight management unit and a Neo 3 GPS module as the positioning system. Mission Planner software is used as the ground station software to monitor required real-time flight parameters, such as battery voltage, airspeed, altitude, satellite count, and heading. Our communication system is composed of a Taranis QX7 radio and a Holybro telemetry V3 operating at 433 MHz, transmitting data between GCS and autopilot using Mavlink protocol. High-gain antennas are incorporated to increase the telemetry range up to 1.37 miles. For obstacle avoidance, the team uses 6 Bennewick TF Mini S LiDARs having a detection range of 39 feet and a field of view of 2 degrees each. Object detection is done through a Tarot 10XP per camera mounted on a 3-axis gimbal. The feed is sent to a Jetson Nano being utilized as a companion computer. The custom-designed pin-release payload dropping mechanism has also been 3D printed in-house using PLA filament.
Our drone is equipped with a Tarot Peeper TL10800 camera which comes with a 3-axis gimbal for stable footage capture and is capable of 10 times optical zoom. It can record videos at 1080p 60 fps, transmitting them through HDMI 1.4 port to the NVIDIA Jetson Nano for real-time computer vision processing. Our chosen camera has a focal length between 10 mm and 300 mm, an image sensor of size 4.8 x 3.6 mm, and a video resolution of 1920 x 1080 pixels. An aspect ratio of 16:9 for video means the effective sensor size will be 4.8 x 2.7 mm. Taking a working distance of 82 feet and maximum focal length means an area of 0.4 x 0.225 on the ground will be covered by our video frame of 1920 x 1080 pixels. Therefore, it is reasonable to say a paper size of 0.216 x 0.279 meters can be easily resolved by our camera. The YOLO B7 algorithm has been trained to detect colored shapes and emergent objects, while optical character recognition is used to identify letters. Python's DroneKit library helps control the drone's movement and payload mechanism upon detection. Airdrop mechanism consists of a cylindrical body with 5 compartments on the bottom side to house payload bottles with annular parachutes attached to the bottles. The imaging system identifies the target location, releasing the payload using a servo mechanism that receives a command signal from the companion computer to open the bottom flap by pulling the pin. After thorough testing, it is confirmed that annular parachutes regulate the landing speed and reduce sway, allowing the bottles to drop within the designated 15-foot radius. Less deviation implies it is safe for humans present in the proximity of the drop zone. Our UAV system includes Mission Planner as our GCS software for flight path control and real-time data monitoring. We use a 433 MHz Holy Bro V3 telemetry system with high-gain antennas for reliable data transmission up to 1.37 miles. The system provides real-time data from the UAV, including airspeed, battery voltage, and other critical flight parameters. We use the FR Sky Tyrannus QX7 radio system, which operates at a frequency above the frequencies within the US with a maximum range of 1.24 miles.
Our airframe is a 4.23 feet wide and 2.36 feet tall off-the-shelf product with a hexacopter configuration, having an umbrella folding mechanism for arms. 30mm carbon fiber tubes are used as foldable arms and landing skids, making it a lightweight structure with high strength-to-weight ratio. The components are covered with an aerodynamic casing to reduce drag and protect electronic components from water and dust. The Jetson nanoplate and payload dropping mechanism have been designed and 3D printed beside the application of vibration dampeners for a 3-axis gimbal, battery plate, and flight controller. The system uses a 605X integrated propulsion system which includes MN605S 170 kV brushless DC motors with 22.4 by 8-inch propellers to generate a total lift of 113.8 pound force, giving a thrust-to-weight ratio of 2.8 with a maximum takeoff mass of 40 pounds and a maximum speed of 19.44 knots. A total battery capacity of 12S 30Ah is achieved using two 6S 30Ah lithium-ion batteries to provide a flight time of 40.8 minutes. We are using Alpha 60A HV ESCs with a current draw rating of 60 amps to regulate the speed of the motors. These ESCs store redundant kinetic energy from unpowered rotating motors to charge the battery. The CUAV X7 Plus flight controller has been chosen to give Altair complete autonomy. By minimizing vibrations, the controller's inbuilt shock absorption system enables the drone to absorb shocks and withstand harsh maneuvers during flight. The high-performance processor and onboard sensors make it a capable flight controller. The CUAV X7 Plus weighs 101 grams and operates at a wide temperature range of -20 to 80 degrees Celsius. It also has two GPS ports for precise positioning and navigation, besides a power module and battery monitor to ensure optimal battery operation. We selected Mission Planner as our ground control station software to facilitate autonomous flight path planning. During the flight, Mission Planner records and displays critical flight data such as altitude, airspeed, satellite count, and battery voltage in real time. Additionally, calibration of the GPS, accelerometer, electronic speed controllers, and radio controller is performed within the Mission Planner software at GCS. 6 Bennewick TF Mini S LiDARs are positioned on each rod of the hexacopter to minimize blind spots. The LiDARs are connected to the flight controller via the I2C port. The algorithm used for obstacle avoidance using LiDARs is ArduPilot's built-in bendy ruler algorithm. It is not the shortest path algorithm, rather, it simply searches a set distance around the vehicle looking for open spaces and chooses a path to follow based on sufficient open space, while also ensuring that the copter is headed towards the destination. During conceptual design, we researched various designs which met our requirements. These included fixed-wing, hybrid, and multi-copter configurations. Fixed wings have longer flight time and range, but they're unsuitable for object detection due to the risks associated with cruising, takeoff, and landing. Hybrids, on the other hand, have limited maneuverability, higher battery consumption, and are unstable during transition in the flight, while the multi-copter configuration is the most suitable, as it can easily navigate through confined spaces for static and dynamic obstacle avoidance. Its lower speeds provide higher accuracy while capturing images and dropping payloads. So, following a detailed analysis of the mission requirements, a hexacopter was selected as the airframe. It has more payload capacity and better flight stability than a quadcopter and is less expensive than an octocopter. It can continue flying even if one of its motors fail, as the remaining 5 motors compensate for the loss. We also conceptualized several options for payload drop mechanisms, including pin release, servo winch, and electromagnetic mechanism. The servo and winch mechanism provides precise control over payload delivery, but adds additional weight complexity and the potential for mechanical failure. Electromagnets can be very effective, however, they're quite bulky and may interfere with drone electronics. While the pin release servo mechanism was selected as it is flexible and simple to use, it is also cost effective and can safely carry a variety of payloads. As for the safe and secure landing of our payload, we selected annular parachutes over hexagonal ones, as they're stable with reduced oscillations and less sway, resulting in better accuracy. A flight termination system has been incorporated with a return to land response after 30 seconds of communications loss. Wire connections are properly soldered and covered with heat shrinks to prevent short circuits that could lead to a fire. Batteries are transported in LiPo bags, and high-quality battery chargers are used to minimize the risks of outbursts, while battery monitors are used to monitor any excessive current draw from batteries and take prompt actions. Cooling fans with acrylic casing are used to prevent overheating of processing components such as the Jetson Nano. A safety switch is used to prevent motors from starting by mistake until it is armed using mission planner or remote control. Digital servos prevent malfunction and provide the required torque and avoid any slippage. Nylon insert lock nut fasteners are used. They have blue nylon rings inside them that create friction with the bolts and keep the nuts from coming loose due to vibrations or other movements. The use of washers in drone assembly allow for load distribution, alignment, and reduction in vibrations.
The camera was calibrated and extensively tested for reliable imaging. The train model for ODLC was tested on 500 images and 5 aerial videos both on and off the flight. It gave an accuracy of 80 to 98% for shapes and colors, 90% for letters, and 80 to 90% for emergent objects, while providing an average object resolution of 120 x 120 pixels in the image. The steps taken to ensure the best image quality include using an onboard computer for object detection to avoid the delays encountered in streaming data to and from GCS, taking images or recording videos while hovering at very low speeds, and using 5 to 10% of overlap during area search for better results. Rigorous airdrop testing via manual and autonomous flight modes was done from height ranges of 75 to 100 feet to optimize the angular shape of the parachute in a way that increased the efficiency of the drop location and decreased the touchdown velocity. The optimization decreased the error rate from 50% to 20%. The payload drop test was performed 25 times, out of which 22 were a success. The average distance of bottles from the center of the 15-foot radius was 5 feet, while the maximum distance was 8 feet. Our unmanned aerial system uses a telemetry system with a bandwidth of 1.7 MHz, allowing us to transmit and receive data efficiently. The system has a bitrate of 921,600 bits per second, which enables us to transfer large amounts of data quickly. However, there is an expected packet loss of less than 2%. 15 full 12-mile test flights to assess aircraft performance. Motor thrust tests showed a total lift capacity of 110 pound-force. PID values were adjusted to maximize waypoint accuracy. 40 test flights over 22 hours covered 280 waypoints with a recorded maximum deviation of 4 feet. A geofence was set up to prevent the UAV from crossing mission flight boundary or flying above 400 feet. Tests conducted showed an above 85% success rate for both cases. The flight path was generated accordingly after testing the waypoint accuracy with 280 waypoints for 12.5 hours over 20 flights. The flight was also rigorously tested after the implementation of the obstacle avoidance program. 6 fail-safes were set up and tested in 8 flights over 4 hours to ensure their proper working. Percentage of their success is shown in the table, maintaining a minimum height of 80 feet. Obstacle avoidance was tested in 2 parts, on static objects and dynamic objects. Static obstacle testing was done initially using virtual objects in Mission Planner. Later, testing was conducted on real objects. Out of 20 tests, 16 were successful. Moreover, our drone avoided most of the dynamic obstacles. Out of 45 obstacles, it avoided 38 obstacles. The team completed 15 full missions, with all subsystems integrated into Altair to test imaging and ODLC, airdrop, communications, aircraft, and obstacle avoidance systems. Inefficient areas in the systems were fixed. 10 objects were placed over an area of 194,000 square feet for searching. Across 15 flights, the team achieved 70% accuracy in object identification. The payload landed safely within 15 feet of the target area around 90% of the time. Timeline scored an average of 100%, with 15 minutes to set up, 30 minutes for the mission, and 10 minutes for teardown. Altair flew over 280 waypoints with an accuracy of 95% and avoided 85% of the obstacles successfully. With 100% in the timeline, 70% in the imaging and ODLC task, 90% in the airdrop task, 85% in obstacle avoidance, and 100% in autonomous flight, the team got a total average score of 89%.
In conclusion, Altair has proven to be capable of performing all the required tasks with decent confidence levels. It can fly more than 12 miles on a single charge with the payload, can detect ground markers with 70% confidence, and can avoid mid-air collision with 85% using its LiDAR systems. We're excited about the competitions and we believe it will perform well in all domains.